Hi guys, today we're talking about position, velocity, and acceleration. This is section 3.1. In this section, there are some terms that you need to be very familiar with. Position, velocity, and acceleration. Position is going to give us the location of an object at time t, and when we calculate the velocity, we're looking at the rate of change of position. So this is just going to be the derivative of the position function, and we'll usually notate that as v of t. Now with velocity, this is speed with direction. So when we're talking about a positive direction, this is indicating that the object is moving either upward or to the right. If we have a negative velocity, the object is moving downward or to the left. The acceleration function is the rate of change of the rate of change. So this is the derivative of the velocity. So we'll usually notate this with a of t, but a of t is equal to v prime of t, which is equal to s double prime of t. So your initial position is where you're starting, that's at time 0. S sub 0 just means the position at time 0. The initial velocity is your starting velocity at time 0. We notate that with v sub 0. Speed is going to be the absolute value of the velocity function. So this is just going to give us speed without direction. So it just tells us how fast an object is going without the direction. Displacement is the net change in position. So it's the final position minus the original position. And our total distance is going to take into account all the direction changes. Next slide. All right, so let's see an example here. So if our position function is t cubed plus t, and we want to find the velocity and the acceleration, essentially all we're doing is taking the derivative twice. So v of t is equal to s prime of t. And this is just using our power rule. So our t cubed, we bring the power in front, and then power minus 1 would give us t squared, plus this has a power of 1. So our derivative is going to bring the 1 down in front, and then t to the 1 minus 1 would give us t to the 0 or 1. So this is our velocity function, 3t squared plus 1. The acceleration is going to be the derivative of the velocity, which is the derivative, the second derivative, of the position function. So the derivative of the velocity function, again, we're just using our power rule. The derivative of 3t squared is 6t. And the derivative of a constant is always 0. So we have acceleration is 6t, velocity is 3t squared plus 1, and our position function is t cubed plus t. All right, let's see another example. Use the position function of an object moving on a horizontal line for examples 2 through 11. So we're going to be using s of t equals 16 t cubed minus 36t squared plus 24 for the next several examples. Our distance will be measured in feet, and time units are measured in seconds. So if this is asking me what the initial position of the object is, so would that be referring to s of t, v of t, or a of t? So s of t is our position function. So if I want my initial position, that is evaluating the position function at time 0. So s of 0, if we plug 0 into our position function, the first two terms are going to 0 out, and our position is going to be 24. And since this is measured in feet, we'll label that as 24 feet. Now, example 3, what is the velocity of the object at t equals 1 second? So this is just finding the derivative of the position function and evaluating that at 1. So v of t is going to be, use our power rule, 16 times 3 is 48, t squared, minus 36 times 2, so 72t, plus the derivative of a constant is 0. So this is our velocity function, and we want to see what our velocity is at time 1 second. So this is like an instantaneous velocity. It's exactly how fast and what direction are we going at 1 second. So we'll just plug in 1 for t, and the result is negative 24. And now this is, the units for this will be feet per second. It's really important that you put your units with these problems. So with position, it's always just going to be feet. With velocity, it will be feet per second. And acceleration will be feet per second squared. Now, what does it mean that we have a negative velocity? So negative is telling us that we're either moving down or to the left. Now, since this said that we're on a horizontal line, that means that we're going to be moving to the left at 24 feet per second. Example 4. What is the speed of the object at t equals 1 second? So remember, speed is the absolute value of the velocity function. So we already found that our velocity at time 1 second is negative 24 feet per second. So our speed will be the absolute value of v of 1, which is 24 feet per second. All right, let's clear this all out. And look at example 5. So example 5 is asking us for the acceleration of an object at t equals 1 second. So recall that our velocity function was 48 t squared minus 72t. To get acceleration is just the derivative of the velocity function. So it's the second derivative of position. So the derivative of 48t squared, again, we're just using our power rule. Pop that power down in front. So 48 times 2 gives me 96. T to the 2 minus 1 would just be power 1 minus 72. And we want to see what the acceleration is at 1 second. So we're going to evaluate this at 1. So we'll get 96 minus 72, which is 24 feet per second squared. Okay, example 6 is asking when is the object at rest. So when an object is at rest, this is asking when the velocity is equal to 0. So to find the time or times when the object is at rest, we're going to take our velocity function and set this equal to 0 and solve for t. So 48, and this is where this is basically just going to be doing some algebra. So we're setting our velocity function equal to 0. This is a quadratic equation. So we need 0 on one side, and we're going to solve this by factoring. That's our first line of attack here. So to factor this, let's look for a GCF. GCF between 48t squared and 72t will be 24t. And then we will have 2t minus 3 left on the inside. So we'll set each factor equal to 0. Let's just come up here to the top. So 24t equals 0. Is at time 0, our object is at rest. And then again at 2t minus 3 equals 0, we'll just solve for t. So we'll get time is 3 over 2. And both of these are seconds. So at time 0 and 1.5 seconds in, our object is at rest. Usually when an object is at rest, it might mean that it's changing direction, but essentially we don't have any speed or direction when we are at rest. All right, let's take a look at the next page. All right, so using the same function that we had initially, this is asking when is this object moving to, oops, let's go back. When is this object moving to the right? So moving to the right is essentially asking us when is the velocity greater than 0. So in the previous example, we found out when the velocity is 0 by setting it equal to 0, factoring and solving. So we know that our velocity equals 0 at t equals 0 and t equals 3/2. So the velocity function is just a quadratic. So I'll erase it down here. I'm going to use this space to write. But our velocity function was 48t squared minus 72t. So we can either do a sign analysis to find out when this is greater than 0, or we can use our knowledge of what the graph of a quadratic looks like. So we know that this is having a 0 at 0 and 1.5. And since our leading coefficient is positive, this is going to be concave up. We don't really care about where the vertex is, like how low this goes. We're just trying to see what portions of this function are greater than 0. So greater than 0, that's asking what values of t are going to give me outputs that are above the x-axis. So our outputs are positive above the x-axis. So this is going to be a span of values. We're moving to the right. Now this can be a little bit tricky here as far as our notation. When you're looking at this, time cannot be negative. So we have a portion of the graph that's above the x-axis that we're not going to be including as part of our solution. All of these values do give me a result, that an output that's positive, but since it's giving me, talking about negative time, we exclude those from our solution. So between time 0 and 3/2, we have negative output. So from time 3/2 and greater, we have positive output. So our object would be moving to the right from time 3/2 to infinity. Okay, so you can write this in inequality notation, or we could write it with interval notation. So 3/2 to infinity. I kind of like this notation a little bit better because it's easier to put our units on there. Part 8, when is the object moving to the left? This is going to be when our velocity is negative, or when the velocity is less than 0. So that is going to be the portion of the graph that is below the x-axis. All of these outputs here are between 0 and 3/2 are giving a negative output. So our object is moving to the left when t is between 0 and 3/2 seconds. Now if you notice, these are non-inclusive inequalities because at time 0 and at time 3/2 our object is at rest. It's not moving to the left or to the right. All right, let's go ahead and clear this and look at example 9. When is the velocity of the object 54 feet per second? So whenever you're asked to find a when, this is referring to time. So that means we're trying to solve for t in our velocity function when the velocity is 54 feet per second. So we're just going to set our velocity function equal to 54. Now for this, this is a quadratic equation, and there's a couple of different ways you could go about solving for t. We could move the 54 over, and we could attempt to factor it. When you try to factor this, it's not going to work out. So you could either use quadratic formula, or you could use your calculator. So in your calculator, you are going to plug this, oops, let's cancel that. You're going to plug this left-hand side in to y1, and you're going to plug 54 into y2, and you'll hit graph, and then we just want to see where these two, the y1 and the y2, intersect. So you can do second calc and choose option 5. And when you choose option 5, it's going to ask you for your first curve, your second curve, and then ask you to guess where the intersection points are. So you should pause the video right now and go ahead and take your calculator out and make sure that you can plug those into your calculator and see where those where the y1 and the y2 intersect. And when you do that, you're looking for a time. So our time is going to be at negative 0.549 seconds, and at time 2.049 seconds. Now, time can't be negative, so this solution would be excluded, and the time when we are at 54 feet per second is at 2.0049 seconds. All right, so let's go ahead and clear this out and look at example 10. So example 10 is asking us the displacement of an object between t equals 0 and t equals 2 seconds. So displacement, if you remember from the beginning slide, is going to be, all right guys, we're almost done with this lesson. The graph to the right shows the position function, so this is s of t, of a radio-controlled car. And we're going to use that graph to answer the questions and explain our thinking. So example 12 asks, was the car going faster at point A or point B? So now when we're talking about whether the car is going faster, you have to remember that this is the graph of the position function. So when we're talking about the how fast the car is going, we would be looking at the velocity. And remember, velocity is the derivative of the position function. And the derivative describes the slope of the tangent line to the curve. So the slope, oops, didn't like that. The slope at A versus that's not a very good graph. Let's kind of get rid of that. The slope at point A is going to be less than the slope, sorry, I'm trying to get used to drawing on this thing, is less, and that's not a perfect little tangent line, it only kind of needs to skim along it, but the slope at point A is less than the slope at point B, so we'd say it's traveling faster at point B, and that's because the curve is steeper. At point B. Okay, which just means that the tangent line is going to have a kind of a steeper slope. So since the velocity is the derivative of the position function, we're going to say it's going faster at point B. Example 13 asks when the car was stopped. So if we think about the derivative, and we're saying that the derivative describes the slope of the tangent line, and if we're looking for when the derivative or the velocity is 0, we'd want to find where on this graph we would essentially have a slope of 0. So all along this curve, our slope for all of the points here would all the way up until C would be positive, and then our curve flattens out. We have a horizontal piece to that. And what would be the slope of a horizontal line? That would be 0. And then we have negative slope from D to F. So the car is stopped between C and D. At which point is the car's velocity the greatest? Now, when we're talking about velocity, Remember, that is speed with direction. So our velocity is going to be the greatest at point B, because the slope of the position graph is greatest at point B. This is where the slope is the greatest. Okay, versus if it's asking us at which point the car's speed is the greatest. So speed is the absolute value of the velocity function. So we can see that between, like to the right of point D, our slope is going to be negative, but it is steeper than it was at point B. So the absolute value of the slope of the position graph is going to be greatest at point E. Okay, this is the absolute value of the slope. So we'll have the greatest speed will happen at point E. All right, last example. Let's go ahead and clear this and move to the next slide. So we're going to talk about vertical motion examples. So we're looking at a new position function. This is s of t equals negative 16t squared plus 48t plus 160. This is going to give the position in feet above the ground for a ball thrown into the air from the top of a high cliff. So our time is measured in seconds and our position is measured in feet. So if we want to find the initial, let me go back to that. And there we go. All right, so to find the initial velocity, this is where v of t, we have to first find v of t and then plug in time is 0. So initial velocity is at time 0. So we have our position function. So to get our velocity function, that is the derivative of the position. And all of these are just going to be using our power rule. So derivative of negative 16t squared is negative 32t, plus the derivative of 48t is 48. Derivative of a constant is always going to be 0. So our initial velocity is v of 0. If we plug 0 into our velocity function, negative 32 times 0 is 0, plus 48 is 48. And please make sure that you always put the units on. This is feet per second. All right, example 17 asks, at what time does the ball hit the ground? So when it's asking you to find time, we're looking for t, and it's asking when it will hit the ground. So does that go with velocity, or would that be a position? So when it's actually on the ground, this is referring to when the position of the ball is 0. So we're just going to take our position function, t squared plus 48t plus 160, and that looks like an 8, that's 60, and set that equal to 0. So this is a quadratic equation, so we want to factor. Every time you factor, you want to start with a GCF, and this we can take out a negative 16 from all three terms, so this is t squared minus 3t minus 10 equals 0. And then we can go ahead and just divide that negative 16 off and factor out our t squared minus 3t minus 10. And our factors would be t minus 5 and t plus 2 equals 0. So we'll just set each factor equal to 0. We get t equals 5 seconds. And t equals -2 seconds. Now we can't have negative time, so we'll exclude that solution. So at time t equals 5 seconds is when the ball is on the ground. That's how long it took to hit the ground. All right, let's erase this and look at example 18. All right, example 18 asks, at what time, so we're looking for t, does the ball reach its maximum height? So at what time does the ball reach its maximum height? Okay, so there's a couple of different ways to do this. The way that you learned how to do this problem in secondary 2H and possibly 3H was to look at the position function. And if you notice, it has a negative, so the position function is going to be concave down, and our maximum height is going to be at the vertex. So in 2H and 3H, you learned to find the vertex of that function using negative b over 2a and then f of negative b over 2a. Now the calculus way to think about this is what is happening to our object at this maximum height. Do you see how it's like we have a position change, and at this point the slope of the tangent line is 0. So the calculus way to figure out when we have a maximum height is to figure out when our velocity is equal to 0. So this is going to be a little bit quicker. So we'll take our position function, and we've already calculated the velocity, or found the velocity function was -32t plus 48. So we are just going to set that equal to 0. Essentially find out at what time do we have this maximum height happening. So we'll subtract the 48 and divide by 32. So time equals -48 over -32, which is 1.5. And please, please, please remember to label your units. So we have a maximum height at time 1.5. Now if I wanted to know what the actual maximum height is, we would take 1.5 and plug it into the position function, because that's going to tell me what my height actually is at that time. Alright guys, so that's it for this lesson. Make sure that you go through all of this and come to class with any questions you might have. We'll have a quick quiz on this, just to the level to make sure that you've actually watched the video and taken notes on this, and then in class we'll work on the homework. All right, have a great day. Thanks.